and we'll get going. And I think Tiago's all ready to start. So thanks, and I hope you enjoy your day.
Okay, hi, good morning. So this will be the non-visual access and web accessibility session. Welcome. We have one communication paper and 3 technical papers. We will change the order of the 2 last papers of the session due to some technical arrangements here. And we will start without further ado with the usability evaluation of 2 virtual aids to enhance cursor accessibility for motor-impaired users. This is a communication paper and will be presented by Eduardo Pérez.
Thank you very much, Tiago, for your introduction, and good morning, everybody. My name is Eduardo Pérez, and I'm coming from the Ecoquitus Research Group at the University of the Basque Country. The work that I'm going to present is entitled a usability evaluation of 2 virtual aids to enhance cursor accessibility for people with motor impairments, and has been done in collaboration between Xabier, Valencia, Myriam, Arrue, Julio, Abascal, and myself. Well, first of all, I'm going to explain what has been the motivation for doing this work. Pointing and clicking tasks are fundamental actions for web browsing when interacting with an on-screen moving cursor, but those actions can be very challenging for users with lack of dexterity in their hands or arms. In addition, motor-impaired users can face many different problems with standard input devices requiring the use of assistive technologies for accessing the web. For instance, joystick, trackballs, or even a keyboard numeric keypad can be used as a pointing and clicking interface. And during a previous work with 11 motor-impaired users, we found that depending on the assistive technology the user was using, the user group faced different problems. For example, joystick and trackball users were less accurate when pointing near a link, whereas keyboard users were more affected by the target distance. Based on these findings and on the literature, we designed and implemented 2 different cursor aids as browser plugins. The first one, we call it the circular cursor, and aims at assisting joystick and trackball users by reducing the accuracy required for clicking. The second one, that we call the cross cursor, aims at assisting keyboard users by reducing the target distance for pointing. Both pictures on this slide show each cursor aid behavior while moving near 2 links. The circular cursor on the left enables clicking the highlighted link without needing to place the cursor over it. On the other hand, the cross cursor shows a vertical and an horizontal line converging on the cursor and moving along it. Links virtually crossed by those lines get assigned a letter for keyboard direct access. Now I'm going to talk about the experimental setting. 3 cursors were tested: the circular cursor and the cross cursor, and also the unassisted original one. 2 websites were used as a stimuli. A third website was used for training purposes, so participants could get familiarized with the new cursor variant. 2 kinds of tasks were defined: searching tasks and target acquisition tasks that should be made with each cursor variant. After finishing each cursor variant, participants were asked to rate it by 8 categories with a 7-point Likert scale. Categories were learnable, rememberable, accurate, easy to use, effortless, natural, fun, and not frustrating. After completing all tasks with each cursor, participants were asked to rank the 3 cursor variants in terms of the overall preferred option for web browsing. Now I'm going to present the study participants. 50 subjects participate on this study. 9 of them were motor impaired and 6 of them able-bodied. Based on the pointing device they used, we defined 3 groups. A first group of keyboard users with 4 participants. A second group of joystick and trackball users with 4 joysticks users and 1 trackball user. And a mouse user group with 6 mouse users. The first 2 groups were users with motor impairments, and the mouse user group were the able-bodied group. All of the users were expert users with the pointing device used during the experiment. And next I'm going to present the results for each of the 8 categories mentioned before. For the learnable category, we got that the circular cursor was highly rated by every user group, and in contrast the cross cursor was highly rated only by the keyboard user group. For the rememberable category, the original cursor get best results as expected, but also both cursor heads were highly rated by all groups. On the next category, the accurate category, the circular cursor was especially highly rated by the motor impaired, whereas the cross cursor got best assessment from the keyboard user group. The original unassisted cursor in this category was negatively rated by several motor impaired participants. For the easy of use category, the circular cursor was the best rated variant by motor impaired. The next category was the effortless category. The circular cursor was the preferred option for joystick and trackball users. The cross cursor was, on the other hand, the preferred option for keyboard users, and the unassisted cursor was only preferred by the mouse cursor group. For the natural category, the unassisted cursor was preferred option by all 3 groups, but followed by the circular cursor and the cross cursor as the third option. For the 7th category, the fun, we got similar means rate for all 3 variants. And lastly, for the non-frustrating category, both cursors and enhancement were very positively rated by each aimed group. The circular cursor by joystick and trackball users, and the cross cursor by keyboard users. In addition, the unassisted cursor showed to be frustrating for several motor impaired users. Finally, the overall ranking shows 2 interesting outcomes. Firstly, motor impaired participants mainly preferred one of the 2 cursor variants. 7 out of 9 selected the circular or the cross as their preferred option for web browsing. And secondly, we got opposing assessments for cursor variants depending on the pointing device used. The cross cursor was the third option for unanimously the joystick and trackball users, while it was the preferred choice for keyboard users. Finally, for concluding, we can state that based on usability responses, both virtual ads proved to be useful and accepted by motor impaired participants. It also has been proved that virtual ads for improving web browsing to motor impaired is something important. As for the future work, we plan to analyze additional interaction data gathered along the experiments in order to study different performance indicators. Due to the interest of some participants, we also plan to install these cursor ads on their computers so we could get better feedback from them and perform further analysis on their interaction. Thank you very much, and I will be pleased to answer any questions you have.
Thank you, Eduardo. Sorry for standing there, but I had to to see if it worked. So we do have time for questions. Yes.
Can you say something about the?
Okay.
I was just curious. I read the paper and I was a little bit confused how the cross cursor worked. Do you by any chance have a short video or can you demonstrate it? If not, I can look at it later. The cross cursor had multiple interactions.
The cross cursor are the two lines that it was shown in the picture. There is a vertical line and an horizontal that follows the cursor movement. And when one of these lines crosses a link, the space that the link represent on the screen, the system assigns a letter to that link and puts a letter near the link. So the user knows that pressing that key, he can click that link.
Yeah, that makes a lot more sense. I couldn't quite figure it out.
Good question. Can you speak to how many links on a page that some of these experiments were done with? And what would happen if the number of targets on a page that somebody could click on were to increase?
The main problems that we got is, or differences, is when the links are too close or there are more space between links. The study was done in 2 pages. One is an informational page and another is a governmental one. And there are real pages with links everywhere. And some of the participants show this issue, that when it was easy for them when links were differently configured. It depends on the position of the links. That would be further study. Yes.
Anyone else? Okay, I do have one. So, as I understood, you only try this with pointing devices. Have you considered how transferable it is to touchscreen devices? If it would be just using pointing with one finger?
With touch interaction, my colleague Xabi he's trying some things, but not the cross one. Instead, the circular one, but not showing the circle. But it's something that is already been studied, that when clicking somewhere near the link can activate it, yes. And if there are several links together, it can be zoomed, the area of so it's bigger and there are more separate, the links get more separated, yes.
I have one more. So the other thing is that you have the second method. It requires pointing and also going to the keyboard for a letter.
That's it.
Have you considered gesturing, for example? Like I select, I go to the link, and then instead of appearing the letters, directions appear. Just use one device, because I think that.
But you say with keyboard, or because there are users
with
that.
a pointing device, even with a pointing device. So it's just a suggestion. I don't know if it would be better. Or not.
That near the link you say that appears
Instead of appearing like the P and the Q as you have in your image, it could be like arrow up and arrow down, and then if I make a movement towards it could help. Just to maintain just one single device, because I imagine that some people could have a problem in pointing and going to the keyboard.
Yeah. Yeah.
So, okay. Well, let's thank Eduardo once again. Okay, now let's welcome our second speaker, Ravi Kuber from UMBC. And he's presenting an empirical investigation of the situational-induced impairments experienced by blind mobile device users. Go ahead.
Okay. Thanks. Good morning, everyone. My name is Ravi. I'm from the University of Maryland, Baltimore County. The work was conducted by my student, Ali Abdolrahmani, who couldn't be here today, but has graciously agreed to model himself in some of the photographs on the slide to better illustrate what some of the challenges that some users who are blind go through when they're situationally impaired. The work was also conducted with Amy Hurst, also at UMBC. The title of the presentation is An Empirical Investigation of the Situationally Induced Impairments Experienced by Mobile Device Users. Okay, so as mobile devices become more advanced and kind of improve in fidelity, they offer a lot more promise for performing tasks while on the go. So for example, accessing email, the web, apps. Unfortunately, what we call situationally induced impairments can often be experienced when using a mobile device. So for example, if you're using the phone while you're in a noisy environment, or perhaps while the user is in motion, the situation itself can kind of put constraints on the user, particularly in terms of their vision, attention, or even motor ability too. So to give you an example, for example, a user who's ambulatory or walking may be trying to use the phone at the same time, but unfortunately by focusing so much on the phone that they're using, they might kind of disregard the scenarios or the settings around them and inadvertently walk into the path of hazards or traffic. Not to mention that if that does happen, obviously their phone-based tasks or the text message they were typing would probably go wrong as well. So there are a few issues that can happen as a result of a situational impairment. Situational impairments differ a little bit from what we call health-induced impairments, as generally situational impairments can happen to anyone irrespective of their sensory, physical, or motor abilities that they actually have. Okay, so much of the research focusing on situational impairments or SIIDs focuses on the needs of young healthy users predominantly. There hasn't been much work actually looking at the needs of people with disabilities. So our research has begun to look at the needs of individuals with disabilities, specifically people with visual disabilities. And just to give you an example of an issue that may affect some users with visual disabilities, if you're walking through a noisy shopping mall and you're trying, you get a message on your phone, it would be very difficult for a user to actually detect the auditory beep because of the ambient noise in the shopping mall itself. For a sighted user, they might be able to see the visual screen flashing or a little envelope icon or whatever appearing on your screen. For a blind user, it's more of a challenge if they can't hear the actual sound coming from the screen. So that might just give you an idea of some of the situational impairments. Okay, so in our research anyway, we focused on the day-to-day challenges faced by individuals who are blind. And we wanted to identify some of the situations, contexts, or environments that may affect their interaction with the mobile device. The idea was by being able to understand some of the challenges they encountered, workarounds that they used, and perhaps improvements that they suggested, we could offer guidance to interface developers who are trying to develop mobile devices or mobile interfaces specifically with blind users in mind. To do this, we conducted interviews with 8 visually impaired or specifically legally blind participants. And to do this, we presented 3 scenarios of situational impairments that were loosely based on findings from prior work from other researchers. To give you an idea of some of the scenarios we asked, we specifically presented scenarios capturing frequent and infrequent tasks that some blind users may face when they're actually using a mobile device in perhaps a public area. So specifically, we focus on the 3 scenarios of using a phone or not being able to use a phone on public transport, in a shopping scenario, and also using a mobile device in a meeting scenario. Just to give an example of the scenario on the board, this is what we presented to the participants just to gather some information. John is a 30-year-old blind adult who uses a cane for wayfinding. He regularly goes shopping, taking a bus to the grocery store from his home. After shopping, he walks back to the bus station with bags in his hands. While walking, he finds it difficult to use his mobile phone in order to respond to a message, make a phone call, or even check the bus schedule. 3 tasks that perhaps users, whether they're sighted or blind, would perhaps want to do. Okay, so in terms of our participants, we recruited 8 participants who described themselves as legally blind. Specifically for our study, we were looking for people with very limited vision or no vision at all, so ideally that they couldn't focus on their level of residual vision. They were all aged between 20 and 49. I think we had 4 males, 4 females. 5 described themselves as blind from birth or congenitally blind. 3 described themselves as adventitiously blind. All of our users had used the mobile devices with a screen reader or happened to be iPhone users using VoiceOver. To reach a wider range of participants that we'd normally get, we tried to employ something called snowball sampling, where we asked our participants to suggest their friends who might not necessarily be on the same mailing list that we were recruiting from. This was our hope to try and find perhaps slightly less tech-savvy people to try and interview with, but we ended up with mostly tech-savvy people, actually, so yeah. So the data we gathered was coded, analyzed, and then kind of divided into themes. And the table on the screen in front of us actually describes some of the themes, and I'll describe most of them in detail for as long as time permits anyway. So the main issue that people mentioned, obviously, was using a phone while ambulatory or while walking, whilst also traversing using a cane. For those of you guys who haven't really kind of encountered what users need to do with a cane, the process of using a long cane is often very active in itself, that users are continuously swiping or maybe even tapping the ground to get information about the environment around them, perhaps looking for hazards or trying to develop a structural representation in people's minds about the actual route they're traversing. We found that responses varied, and I've got a couple of quotes on the board. Firstly, from users who were kind of a little less tech-savvy about using phones. Particularly this one user, participant 1, favoured not using the phone at all when she was walking. She said that she preferred to keep the phone in her purse so she can keep her attention solely on what the cane is actually trying to identify in front of her, so that she won't make mistakes or deviate into the patterns of traffic by mistake. Participant 2, who was a little bit more tech-savvy, found that due to conditions of his work, it was necessary for him to be able to take phone calls while travelling on public transport. Because he lived in a busy city, he was very worried about using his phone whilst exiting a subway station, purely because he thought that if he momentarily stopped to focus on the phone, the volume of people behind him might actually knock him over or push him out of the way, probably a very unfriendly city. So as a result, he favoured trying to navigate to very kind of quiet locations within the subway station, if those exist, to try and attend to the actual call itself. However, by going to locate some kind of quieter areas within the subway station, it was taking him away from his regular route and would obviously add time to the journey. Okay. 3 of our participants were very aware that sighted users were able to use the phone while walking, whether safely or dangerously, and were kind of found it a bit unfortunate that maybe the case may be a little bit harder when using a screen reader to be ambulatory and also use a screen reader at the same time. What they highlighted for us is that the process isn't as simple for individuals who are blind. Firstly, if an individual who's blind is using a cane or perhaps has a service animal, one of the hands will be encumbered with the actual cane itself or the leash, and as a result they will be concentrating with that hand on what exactly the cane is kind of looking at or where the leash is moving. The other thing is that if the phone is in the other hand, gestures made using the screen reader can sometimes require 2 or 3 fingers to actually interact with the screen itself, and the process of holding the phone one-handed while using those 2 or 3 finger gesture commands can be a bit challenging for some users. While some users may manage, others may find it difficult, which can be a little bit of an issue. In terms of workarounds, one user told us that they had found one way to use the phone one-handed would be to actually strategically reposition some of the icons on the screen to in close proximity of where the thumb would be. This took a little bit of skill to actually try and manipulate the actual position of the icons, but it pretty much allowed them to think, okay, we'll probably get closer to the app that we're trying to actually locate at the time. Participants also talked about issues riding public transport, and some of these issues also affect sighted users too. A number of our participants told us that they were unsure about the other riders' intentions behind them. So if they did use their phone, they were a little bit worried that maybe, information would be shoulder surfed from behind, so, sighted users would be able to see what they were doing and maybe copy their data in some kind of way, or even steal the phone to a certain extent. Other users favoured more privacy and opted not to use their technologies too much, or only when necessary on public transport. Furthermore, noise levels may impact voice dictation, and as a result, users were trying to use the autocorrect functionality on phones, which wasn't always found to work as effectively as the user wanted, meaning that they spent a lot of time with autocorrect. The bumpiness of the ride on public transport also impacted users' ability to type or select characters. The fingers would unintentionally slip, and as a result, more time would be spent with autocorrect too. One of our participants mentioned that he'd often wait till he got off the bus to check his actual messages, but often he would end up forgetting that he actually received notifications while on the bus, and then it may take a bit of time for him to actually respond to them. Whereas as sighted users, we can generally glance at our inboxes just to identify which messages are new. The case may be difficult for perhaps slightly less tech-savvy individuals who are blind and new to screen readers, who may find that they go through things very sequentially. It may be a little bit of a challenge for some users. Other issues that came up, certainly during inclement weather, some of our blind participants suggested that they wore gloves or hats, and as a result, it could be a little bit more of a challenge to interact with the screen reader unless they had specially customized gloves with missing the actual parts or tops on the finger to actually interact with the phone itself. And certainly on a windy day, the howling sound of the wind could impact voice dictation to a certain extent. Some of our other users talked about other encumbrances which perhaps sighted users may enjoy. So to a certain extent, it was very hard for some of our participants to go shopping and carry shopping bags at the same time as trying to traverse with a cane and use the phone at the same time, purely because when you're actually encumbered with that many items, it's very tough to actually use the phone one-handed to actually try and perform the tasks that you need. It forced a lot of users to just respond to urgent calls, either by putting the bags on the ground at some point when they were leaving a grocery store, or to just wait till they got home. So it was obviously that their behavior was actually changing. But there was some fear by some users that if they put their bags on the ground and they were unsure about the ground around them, the bags themselves would get dirty or muddy. And as a result, people were favoring not taking calls while they were, en route, or had gone to other extremes or other kind of, had other workarounds, like for example, carrying all items in a backpack, just to make sure that their hands were free for using the cane and using the phone if they were able to. Okay, so in the interest of time, I'll just move forward a little bit. Users also talked about unfamiliar environments as well, where they were trying to explore with the cane to kind of try and make a mental structural representation of the environment around them. They suggested that, a lot of cognitive effort needed to go to explore the environment, but also obstacles in the way like curbs or sidewalks, or perhaps, different slopes, etc. If the weather was inhospitable or inclement, like for example, it had been raining or snowing, for example, they would obviously, take a little bit more care with where they were stepping, and obviously using a phone at the same time could be a bit of a challenge. Other things that blind users mentioned, particularly using the phone in things like meetings, could be a bit of a challenge, because sighted users would be very aware that the blind user may not necessarily be focusing on the meeting when they're looking at their phone to look at the time or the missed call that they got. And as a result, some of our blind users were very conscious that they didn't want to look out of place with sighted users, which could be a bit of a challenge. Some blind users actually said that wearing earphones may appear as rude to other sighted users, even though that they were just doing exactly the same tasks that sighted users were doing, covertly trying to glance at their phone to determine how much time was left in a meeting. Yeah, the last issue that was identified was issues with photographs and taking photographs. So obviously blind users obviously take photographs for a variety of reasons, either to share with others or to identify signposts or things that they want to ask for assistance with. Unfortunately, many of our users felt that feedback coming from these apps was too late, and they felt that they should get feedback slightly earlier. So for example, the user may take a photograph only to find out once they've taken the photograph that the levels of lighting or the angle was inappropriate, and computer vision might not be able to understand what exactly the image is, or a third party may not be able to understand what the image is, and that was considered to be a bit of a challenge. We asked the participants to suggest improvements. They came up with 4 main improvements for improving interaction. So they suggested considering some of the needs that blind users face, and in certain situations voice input may be the only strategy forward for them. If that's the case, then ideally ambient sound shouldn't interfere with speech input where at all possible. Feedback should be a little bit more frequent, or feedback should be a little bit more early, especially with things like when you're taking photographs, not once the user has actually finished a task. And phones are smart enough to actually understand user context as well. So the idea is that if the phone itself, using the accelerometer or gyroscope, can actually detect that the user is encumbered with something in the hands, perhaps it could adjust settings on the actual interface itself to better support a blind user in those scenarios. Our insights from the research just offered a few kind of guidelines to interface developers. Certainly, the main issue that came up was considering interaction modes. Blind users would also like to do tasks one-handed. Some users can manage, other users cannot, by what we found anyway. If that's the case, 2 or 3 finger gestures for voiceover may not be the most practical when the user is ambulatory or walking. They also talked about ways of actually limiting errors and reducing errors, particularly with autocorrect. This is a problem for sighted users too, but it can be a little bit more of a challenge for blind users. If interface designers could just take this into account, particularly during the testing process, that would be a benefit. Other things that blind users mentioned were evaluating in realistic settings. It was very obvious that some technologies hadn't been tested in the presence of distractors, like auditory distractors, or when the user is in motion, and certainly phone interfaces should be tested in those kind of scenarios. Lastly, the people didn't really want to look different from others, particularly when they wanted to check their phone covertly, especially in a meeting or a class. It was something that people wanted to do things without kind of appearing rude or different from one another. Okay, so in terms of our future work, we're hoping to extend the study by examining the interactions of people in the wild, just to find out what kind of challenges they experience and to better cement the information we have. And hopefully we'll be doing some kind of co-design to see whether we can design solutions for situational impairments. If anyone's interested in some of the work, we've got some more guidelines in the paper, and a student, Ali, who graciously modelled for some of the photographs that you may have seen, can be contacted at the email address aliob1@umbc.edu. Thank you so much for your time. Okay, and we'd like to also thank some of the participants who I found out are actually in this room because of some of the issues with the recruiting. So you guys did an amazing job. Thank you so much.
Thank you, Ravi.
Sure.
Questions? No questions. I do have one. So, do you have any of the users commenting the extent to which the new technology is increasing the damage imposed by situational impairments?
So that's a really interesting question. So, I mean, I think out of our participants, we had 7 who described themselves as tech savvy, and only 1 who described themselves as a kind of less tech savvy. That one participant favored just not using her phone anytime she thought that, the scenario may get too challenging in some kind of ways. As technology improves, obviously people get more improved with the actual technology. So I think people are adapting quite well from what we saw. But you're right, as more functions get added, there's more opportunity for distraction. Unfortunately, we all know that we shouldn't really check on messages on our phone when we're driving, but still a lot of people seem to do that. So, you know, there's the danger that human limitations may cause people to, you know, think that they can divide their attention quite effectively when in reality they really shouldn't be, and that can happen for both blind and sighted users. So, okay, thank you.
Okay. There's one other.
Oh, sure, sorry. Hi.
Yeah, just more of a suggestion of a potential future direction for the research would be to look at folks who use guide dogs and to see if there's a difference in cognitive load or just the way they are able to handle the use of a mobile phone as opposed to a human user.
That's a really interesting point. So we had 3 service animal users as a part of the task, but they appeared to be using their phones for. They appeared to be, you know, using the dogs or the animals for slightly different purposes of locating objects around them, or at least that's what they told us. Anyway, it would be really interesting to find out how it differs. I'm actually quite curious. So,
Pretty much focus on people using their phone, and you like they were holding their phone and touching it. At least in practice, one of the things I've found for the last 3 years, I mostly would use my phone one-handed when the phones were smaller. But in the last 3 years, I pretty much used it as a Bluetooth headset. And there are a lot of things you can now do with just a Bluetooth headset, all the way from answering a phone call to making a phone call to, you know, looking up information quickly, where some of these hand usage aspects actually go away. And
Sure.
You never take your phone out.
and just to follow up on that, does the ambient noise get filtered out, or does it cause distortion when you're actually
So
doing
I
that?
actually stick this halfway in my ear like that. So I
Uh-huh.
can still hear everything.
Okay, so you can still hear items
Yeah,
around
so
you.
it does not affect the ambient noise stuff. For a while I thought noise, the aftershock type cold conduction headsets were the answer, and then I realized that they were actually not the answer, because even though they hear your ambient noise perfectly wearing cold conduction headsets, the cognitive load of paying attention to the speed actually loses. So I actually just use a regular headset. It's not over the ear, it's in ear, it's actually half in ear, and actually doesn't fall out. And it actually works remarkably well.
Okay, thank you very much. It could be some future work to look into to find out. So, okay, great.
Thank you, Xabier, again. So, for our third talk in this session, we'll have Jeffrey Begum from CMU presenting the effects of automatic speech.
Erudite, brilliant Juilliard-trained musician.
Sorry.
Quality
You got a nice foreshadowing of the talk.
on human transcription latency. Go ahead.
All right, great. Thank you for that introduction. So today I'm going to be talking about work that my group and I have been working on for the last couple of years, which is how we can effectively combine automatic speech recognition with human computation to more efficiently produce captioning and transcriptions for deaf and hard of hearing people. And this actually, at the start, seemed really obvious. What we thought we could do was just provide the automatic speech recognition output to the human transcriptionists, and that would just make them more efficient, because even if speech recognition isn't perfect, it gets some of the words right, and that should be a good starting point. The talk today is basically our investigation into kind of the subtleties of that, where that happens and where it doesn't. This work is actually led by my PhD student, Yashesh Gaur, who unfortunately, because of visa problems, couldn't be here. But he was responsible for making these very great slides, and usually responsible for making me look good, so I appreciate that. The rest of the team is Walter Lasecki at Michigan, and then his co-advisor at CMU, Florian Metz. All right, so probably this room doesn't need a lot of motivation for this kind of work, but the basic motivation is that there's a lot of audio that's being produced, a lot of speech that's being recorded, and we need to transcribe it to make it accessible. Just as one metric, I think it's true that 100 hours of video are uploaded to YouTube every minute, right? And so that is a huge problem, and when you start thinking about the scale of that problem, it's difficult to think about how we would solve this problem with human transcription alone, and so you start thinking about automatic speech recognition, so having the computer do it or at least help. Automatic speech recognition is basically a process of turning the audio signal, so the computer's representation of what we say, into text, into speech, that transcribes speech. And so here in this example, the ideal case would be someone would say, this machine can recognize speech. And that would go in through this big, complicated process, and out would come, this machine can recognize speech, but in text that the computer can understand. Unfortunately, our computers don't have all of the rich context. They don't have the common sense intelligence that humans do. And so a lot of times you get something more like this. What comes in is this machine can recognize speech, does its feature extraction. It has all of these different things that go into decoding what that means. And then out comes, this machine can wreck a nice beach. Sounds kind of similar. And so in practice, we don't let machines do this when it matters, right? We hire people who do essentially the same thing. They take the audio signal in, this machine can recognize speech, they listen to it, and then they type it. They say this machine can recognize speech, but in text so that the computer can understand it, so that it can be converted to other forms, either visual forms or audio forms. And so like I said, the simple idea that many people have had is, well, why don't we give those human workers the speech recognition output as a starting point? If you've been to W4A before or assets before, you might have seen that Greg Vanderheiden, for instance, has this system where he presents the speech recognition output as captioning and also sends that to some human workers behind the scenes who are correcting it to make it better. I noticed the New York Public Library actually has all of these audio recordings of stories that as part of their community oral history project. And so they're also doing this. So they have this interface where they have some audio and they've automatically transcribed it with speech recognition, and then they're asking people to fix that up. But what is interesting about this is that we for a long time have suspected that the effectiveness of this depends a lot on how good the speech recognition output is, right? So if it's really good, this probably works pretty well. You just fix an error here or there. If it's really bad, it can probably be pretty confusing. And so just to illustrate that, I will try to show a demo. It may or may not work. Let's see. Okay, cool. Oh, wow, it was cool for a second. Okay, there we go. So this is just a box, and you'll hear some audio playing. And I'm going to try, as this audio plays, to type what it says. So this is basically the base condition of me being a human transcriptionist, and I'm going to try to keep up with this audio.
Erudite, brilliant Juilliard-trained musician. Music is medicine. Music changes us. And for Nathaniel, music is sanity.
Sanity, I don't know. So, point being, that was relatively slow speech. As a normal person, I had a very difficult time keeping up with that. I missed some words, I misspelled some words. I'm going to show you another example, which is going to be the same example roughly, except what I've done is I've pre-populated it with speech recognition output. And I'll tell you in advance, this is speech recognition output that is actually near the state of the art for general purpose speech recognition systems, which is about 15% word error rate. And so I'm going to play the same audio now, and instead of trying to type everything, I'm actually going to try to correct it. And just so you don't think I'm cheating here, I just prepared this demo while I was sitting there in the last talk. And so I really don't know how this is going to go, but let's try it. Okay.
Erudite, brilliant Juilliard-trained musician. Music is medicine. Music changes us. And for Nathaniel, music is sanity.
Okay, so that actually kind of worked, right? Like I replaced whatever was at the beginning, which I forget, with erudite. It took me a little bit to figure out like what I was supposed to replace, but fortunately I had that kind of anchor there of this word brilliant that showed up correct in the speech recognition output that then I could kind of get back into sync with what was going on. And so that was 15% word error rate, and I, at least in this particular example, was able to keep up. Here is speech recognition, again, the same thing, but this time it's 45% word error rate, which is actually not that unusual for a bunch of situations where we don't necessarily have a good language model, where the acoustics are bad, or whatever else. And so just so everyone has access to this, the starting transcription is there you guys really, and to the are trained isn't music, these medicine music changes such as for Nathaniel, music is Senate. And so that's 45% word error rate. And now try to play along. You've already heard this clip 3 times, so it's already cheating, but let's try to see if we can do it.
Erudite, brilliant Juilliard-trained musician. Music is medicine. Music changes us. And for Nathaniel, music is sanity.
So basically it was very confusing. For those of you who could not see that, that was just very confusing. So it was very difficult for me to know where I was supposed to be making these changes. I started just basically typing it from scratch anyway. There weren't these anchors because so much of it was wrong. It was really difficult to match what I was hearing to what was being displayed or what had been output by the speech recognizer. And so hopefully this little demo gives you a sense of that the word error rate does actually matter. So you can't just pipe in any old speech recognition output and expect it to make our transcriptionists better. All right, so if I go back to the presentation, the point of this paper was to explore under what conditions that was true. So we have our simple idea. Basically, how good does speech recognition need to be useful, and how do captionists interact with speech recognition output that has errors? So we designed a relatively simple experiment. It kind of looked like what you saw. We had a captioning interface that was much like what you saw with some handy keyboard shortcuts for playing and pausing and going back and forth to kind of eliminate mouse interaction. We used a very popular corpus used in speech recognition research, which is the TED Liam corpus. This is a collection of TED Talks. We used the Quality Speech Recognition Toolkit, which is one of the state-of-the-art deep learning speech recognition systems. And we used it to create speech recognition output with different word error rates. So everywhere from 15%, which is kind of state-of-the-art for general purpose systems, it's actually as good as Quality, the best results with Quality, up to 55% word error rate in 5 percentage point increments. We did this in a fairly ecologically valid way in that we changed the parameters of the speech recognizer, in particular the beam width, so the search space it was looking over. As we made that bigger, we could make it harder for the speech recognizer to find the right output, and so we could have it kind of naturally produce more errors at these different levels. And so we had 16 of these 16 one-minute clips that we did this that we're going to use for the rest of the studies I'll talk about. So the participants decided when the experiment started, so we didn't have to. So we had pretty good timing information, and we also had a qualifying step where we made sure that whatever they provided was within 10% of the ground truth. So we knew the answer to all of these, and so basically they had to keep working with it until they got it to nearly correct. We did first a between subjects experiment where we had our 9 different word error rate conditions and 1 just from scratch condition. We also had an within subjects, which was 9 of these word error rate with the speech recognition output with different word error rates, and 1 from scratch. And we thought that this got at different aspects of the problem, which you'll see in a bit. So one is, so first I'll talk about the results of the between subjects study. And so there's this graph here, and basically it shows that this is latency here on the y-axis goes from about 300 seconds, which is roughly the baseline, the fastest we saw anybody do it, up to about 600 seconds. The x-axis here is the different word error rates of the clips. And so at about 15% word error rate, it was much faster, right? So let's see, the baseline is about 500 seconds. So baseline is about 500 seconds. And transcriptionists did a lot faster when they were given the speech recognition output with high quality. So at 15%, it was almost 150 seconds less. And this trend continued. They were doing better at 20%, 25%. And then at 30%, they got a little bit worse. At 35%, they got even worse. 40%, even worse. 45%, even worse. And then miraculously, they started getting better, right? At 50, as the speech recognition output got worse and worse, they started getting better. Maybe you have a guess about why. Essentially, what they did was they realized that once it got bad enough, they very quickly realized that it was junk, and they just erased it all. And then they started typing from scratch. There's a little bit of time it took them to realize this is junk and erase it, but once they did, then they were back at essentially the from scratch performance. And so there's these like kind of messy looking graphs of these are the length of the transcript over time. And so you can see when the word error rate is pretty low, it kind of just grows. Whereas when it's pretty high, you get all these people jumping down to 0 and then building back up from 0. Let's see. And so that was kind of interesting, right? So this is this interesting interaction between the quality of the speech recognition output and what people do. And then the within subjects study confirmed our threshold, at least for this kind of pool of workers, also finding the approximately 30% word error rate threshold as where for this pool of workers it becomes worse to give them speech recognition output as a starting point. We didn't see the drop down again, and I think it's because in the within subjects experiment we had all of the workers did all of the different conditions, right? And so I think they were kind of tuned into just working with what they had, and so it just kind of got worse and worse and worse. All right, so kind of quick conclusions. While it almost certainly varies based on your pool of transcriptionists, there is a threshold where a threshold for word error rate where providing the speech recognition output is actually worse than starting from scratch. Perhaps not surprising, but we don't see that reflected otherwise in the tools and different approaches that people have produced in the past. In our study, the speech recognition output had to have a word error rate of less than 30% for us to see this benefit. And probably not surprising, but the human kind of interaction with the error-prone speech recognition output is probably important, right? So if you don't want them deleting all of the speech recognition output, you probably should make it good enough that they don't think that would help them. So what does this mean? Well, one thing that we found, this is our future and ongoing work. So one reason why it's slower sometimes to edit the ASR output rather than just starting from scratch is that there's really two parts to what you're doing when you're editing the ASR output. There's the typing, whatever you need to, but there's also finding where in that transcript you should start typing. And so we had a paper at Inner Speech last year where we were trying to eliminate the finding part of that. So what people could do with this alternative interface was whenever they expected to see something in the ASR output that they did not see, they could just type that word and then the system would figure out where is the most likely place for this to appear and stitch it into the speech recognition output. So saving the person the time finding it and only having them have to type it. Another part, which I just have a big box here because we don't have a graphic yet, is that I've been kind of talking about these clips as though the word error rate is uniform across them. But what we know in practice is that the word error rate is fairly bursty, right? So you'll get sections that have a lot of errors, and then you have sections that, for whatever reason, the speech recognizer gets right. And so there might be some way to leverage that, right? So maybe you don't get rid of all of the speech recognition output. Maybe you just, if you could figure out which part was most likely to have the errors, maybe you just get rid of those parts and present. And it's hopefully getting the best of both worlds, where the transcriptionists can benefit from when the speech recognition output is good and not be harmed from when it's bad. Okay. So that's the end. Thank you all. This is Yashesh again, and I'll take any questions you have. Thank you.
Are there questions for Jeff? Go ahead.
So Jeff, were you showing the time alignment in your document?
So we were not. So these are relatively short clips. It's a good idea. So it's showing the time alignment. I don't know how much it would change things.
That's something we created way back actually with Julio capture. It turns out that even if you have a full transcript, the harder problem for the human is actually
Yeah, so what, I mean, obviously what the speech recognizer does output is a timestamp for all of its, when it thinks each one of those words appear. And it might also be getting at kind of what we're doing with the work I mentioned from InterSpeech with once you type a keyword, it'll figure out where to go. Kind of the reverse question. But I do think there's a lot of opportunity for better interfaces, right? So.
The other place you may want to go look for related work is I believe exactly similar work was done in the 90s in the domain of OCR. And you have almost very similar numbers where OCR error rates go to over 10% and slightly faster than like the
Yeah, I haven't seen that work, but I would definitely believe it. Karen, next one.
Jeff, thanks. There's probably a really obvious answer to this question, but I was wondering what happens if instead of trying to correct the errors, all you do is feed back into the speech recognition engine the same audio clip, but with the additional information, this isn't something diet, but brilliant was right. So the human translator just says wrong, right.
Yeah, so we've also explored a little bit with that. The speech recognizer maintains this big, complicated like lattice of its hypotheses that there's two ways you can interact with it. One is just is there an alternative hypothesis that you could just select from? And we tried to come up with, and we're still continuing to try to come up with good interfaces that can support selecting among those hypotheses. One thing that seems to be true, although this is just anecdotal, is that when the speech recognizer is most wrong, which is when you maybe most want to have this work, all of its hypotheses tend to be really wrong. You just get something's messed up and it just repeats that. But definitely, I think there's opportunity there. The other thing that we're trying to do, and this is Yashesh's current work, is to kind of directly manipulate the probabilities in that lattice model, or even add new like arcs and things if they're not there. But it gets kind of tricky. I didn't realize how big and messy these lattices in the speech recognition model were before I started working here. Yeah.
Thanks.
Cool. Thanks, Jeff. Okay, thank you for waiting. And so our last talk in this session is AudioDraw user preferences in non-visual diagram drawing on the touch screen. It's a technical paper and it will be presented by William. Thank you. Go ahead.
Hello, my name is Bill Gressmeyer, and this is a project I worked on with my advisor Elka Former at the University of Nevada, Reno. And this is about non-visual diagram drawing for touchscreens. Okay, so let me just give you some background here. So diagrams are generally inaccessible, but especially creating diagrams is very difficult for blind people. One solution that they use, which is very low tech, are raised line drawing kits, where you have a piece of paper, a pen, and a board, and you push the pen into the board and you can feel the line raise up. This is a low-tech solution. People use it all the time, but the problem is you can't save it in digital format. You can't edit it after you change it. If you make a mistake, you have to start over. And over time, the lines can get flattened. You put them in your backpack, and that's a problem. Another solution that people use are some software like Microsoft Excel, where you can put in data in a spreadsheet and it automatically creates a bar chart for you. But the output's inaccessible, so you can't sit there and look at it and see what you're doing. You need a sighted person to evaluate it. So our solution here is we created 2 iPad apps to help blind people create diagrams on their own. So let me just talk about some related work. Some background research has been done in drawing diagrams, drawing apps in general for blind people. One of them is the grid-based model that was done at UC Berkeley a while back in 2000. What they did was divide the screen on a computer with a keyboard, divide the screen into 3x3 grid, like a telephone pad, and you could select one of the cells of the grid, and a point would be put in the middle of the cell. Then you can select another cell, and then an automatic line would be drawn automatically between them. So for example, you would select the 4 corners of the grid, and you could automatically draw a square. Another research project that was done more recently was Finite Automata, and this was also a keyboard and a computer. And they can move around circles on the screen and connect lines between them. There have been some touchscreen apps. One of them was called T-Draw, but this was more of a freehand drawing app. So the users would place their finger and draw a line, and then they would get text-to-speech feedback and place their finger at another point and draw another line. So the lines were wavy, and they would have to draw each line from each point. That is most of the related work. So let me talk about the design of our initial prototype. So we did 2 prototypes here, and the first one we decided we wanted to focus on STEM education. So we wanted to work on geometry because geometry seemed to work really well for a gestural touchscreen input. So you could select the type of shape you want to draw, for example, a square, a triangle, a rectangle. Those are the 3 shapes we implemented. And then with gestures, you could specify the geometric properties of the shapes. For example, you could place the center of the circle at an XY point in the XY axis, and then drag out with your finger the radius, and you can hear text-to-speech at how long the radius is, 2.33, and then double tap to have it automatically draw the circle with that radius. So here's a screenshot of the app. Here's a triangle, an isosceles triangle, and you can see we have an XY axis on the grid. Before they start selecting shapes, they can put their finger on the grid and hear the XY coordinates with text-to-speech. The drawing part of the app, this is an iPad app. The drawing part of the iPad app does not have voiceover on it, but the buttons at the bottom, they do have voiceover, so the users could select the shapes they wanted. So we did a preliminary evaluation of this app with 2 users, one 23 and another 30, both male, later blind. They really liked the app. They thought it was interesting, but there was some feedback. They thought the app was too specific. It was just for geometry, so you use it in one class in high school or college, and then you have no use for it afterwards. So that was one problem. They also wanted to be able to move around the shapes afterwards, so we didn't have that implemented. And relabeling shapes was another thing they wanted to do, so relabeling the XY axis to whatever numbers they would like. Okay, so our second prototype, we decided to take away the geometry aspect and focus on using predefined shapes without being able to specify the properties. So you could select the predefined shapes. We did, again, a circle, a triangle, and a rectangle. And we took away the XY axis. This time, instead of XY coordinates to figure out where they were on the screen, we used compass directions. So if they're on the right side of the screen, it would say east. They're east of the center of the screen. And it would give some inches information, like they were 1.2 inches away from the center of the screen. They could select the shape and place the shape. Afterwards, they could move the shape if they wanted to move the shape again. They could also center, so they got information from where they are from the center of the screen. Instead, they could select a shape and get information about where they were in relation to that particular shape. And they could also change the direction the shape was facing. So they could have a rectangle facing to the northwest instead of just up, down. So here's a screenshot of the app. We just have a blank screen, another iOS app. Sorry, I accidentally hit a button there. Okay, so here's a screenshot of the slide. Again, there's a drawing surface that VoiceOver doesn't interact with, and at the bottom you have buttons that you can select the shape, save, and exit. That VoiceOver speaks to the users as they're doing it. Okay, so we did a user study on the second prototype with 8 users, 2 female, 6 male, 3 early blind, 5 completely blind, and 3 were low vision, but they use screen readers on a regular basis, so they had no problem using the screen reader. Most of them were, almost all of them were tech savvy, and all of them use a touch screen at one point, except one. That one participant, we decided to let him learn the touch screen on the iPad and play with it for about 30 minutes before he did the user study. So he was able to get caught up pretty quickly. We just showed him the basic stuff, not everything. So how to double tap, move his finger around, hear what's going on. So he had a more difficult time doing the study, but he was able to do it. So our procedure. So the study was really a free-flowing qualitative study. We didn't do any quantitative measurements here. We had the users place several shapes on the screen wherever they liked, move around the shapes, change the direction that shapes were facing. And as they did this, we had them think aloud, give us qualitative feedback, make comments. So that is the procedure we used. And then we had some Likert scale statements. We rated on a 5-point Likert scale from 1 to 5, 1 being extremely disagree, 5 being extremely agree. So here's a bar graph of the results of the Likert scale statements. And I'd like to thank my advisor for making this bar graph for me, because it would be very difficult for me to make it. So as you can see, the positioning technique, this was described simply as being able to move the shape around the screen and place it wherever they want. So they move the finger around, place it up, point, double tap, and drop it there. They rated this very highly. I think it's a 4 here on an average. So they really like this. The other one was compass directions. Some of the users said the compass directions were very interesting because it tied in with mobility training. And so during their mobility training, they also had the compass direction northeast, southwest, northwest. And so that was very useful for them. Changing the direction the shape was facing was easy enough. To change the direction the shape was facing, we simply had the users move their finger around the shape. So if their finger was to the right of the shape, it would point to the east. If it was below the shape, it would point to the south. But one user commented they would like to see the rotor gesture to change the direction the shape was facing, but we had not implemented that. So these are the Likert scale questions, and one user commented that the spatial layout of the screen, we used an iPad mini here, so it was enough screen space to move stuff around, but it wasn't as big as a regular iPad. And they felt that, one user commented that the spatial layout, the spatial physical feeling of the iPad was enough information for them to figure out where they were. They didn't really feel like they needed compass direction or inches information. They can move their finger around, drop an object, move their finger over that object again, hear where it was, place another object, and generally remember where the first one was they placed without much problems. Some more comments and feedback were, we had the buttons at the bottom, but the drawing screen was too close to those buttons, so one user dropped the shape next to the buttons, and he was unable to pick it back up again, and that was just due to a technicality with the app, so the drawing surface needs to be further away from the buttons, or the buttons is to be smaller. But generally the users liked the app. The first user who used it thought it was very cool and said it was a new toy to play with, and we liked it very much. So the participants gave us a lot of new directions to look at. Resizing the shapes was one of them. For example, in the second prototype, we just used an isosceles triangle to move it around the screen. But in the geometry version of the app, you could place the 3 points of the triangle wherever you wanted to create any type of triangle. It'd be more difficult to create an isosceles triangle that way, but you could create any type of triangle. But users suggested being able to resize the shape after they place them. If they wanted an isosceles triangle, they place it, and then they can move the point to the left or right or up to make it bigger, smaller, and so forth. Bimanual interaction was mentioned by one user, being able to place 2 points of a line with 2 fingers so they know exactly how long the line is, or to place 2 shapes at the same time so they get a feel of where the shapes are in relation to each other. Another direction was the first user really wanted to connect the shapes together to snap a triangle onto a square to make something like a house, so it would be a picture. And the last area of future work we wanted to look at was quantitative analysis. So it's very hard to judge timing of how long it takes to create a diagram because different people would create it faster or slower. It'd be hard to create a standard timing. But doing some quantitative data on some real world diagrams like flowcharts would be an interesting area of future work. So that is my presentation. Here's just the conclusion to wrap up what I said. And thank you, and I'll take questions now.
Do we have questions? Lily? Go ahead.
I'm just curious if you did any analysis or anything amongst folks who are Braille users first versus those who aren't, and their what their views were of the decision.
Yeah, that's an interesting question. So we did mention that in the paper. The Braille users here, usually the early blind users, were very interested in having some tactile feedback. They said if they could have a tactile overlay of the XY axis or the grid or something like that, it would be very helpful. Because one user mentioned they were a very tactile person, they liked Braille. They didn't like the speech as much, and they wanted something tactile on the iPad to help them out. So yeah, there is some information there, and you can read more about it in the paper.
I've got a question. It seems like you tested mostly the person building them, but I'm curious if someone else built a really complex diagram, were they able to understand the diagram themselves?
We mostly just had simple shapes moving around the screen, so no complex diagrams were built. But after they were able to place them, the first user had an idea of placing a bunch of shapes in the upper right quadrant and trying to change them to face all the same directions. And so he was able to do that, and he was able to get a sense of where all the shapes were by if he put his finger over the screen and moved it around, once his finger hit a shape, the app would say with text-to-speech what shape it was, triangle number 1, triangle number 2. So he could move his finger around here where everything he made was placed.
So I was wondering whether you were considering using a already existing geometric drawing library as a backend. So one of the things I think of is, for instance, JSX graph.
Yeah, so we just use the automatic drawing functions that come with Objective-C. You basically create one point and it draws a line from one point to the next, to the next, to the next. And you can draw a square triangle easily, and there's a circle drawn out. I initially looked into using OpenGL to create graphics, and including 3D graphics, but OpenGL is very complicated and I didn't know anything about it. And it's very hard for me to program graphics because I'm blind. And I actually like to thank my wife for helping me a lot on this, because she would describe the screen for me every 10 minutes while I was debugging the program. So using more advanced graphic software is very difficult for me, but I would think it would be useful in future development of the app.